Hello and welcome to the module 3 part A. The title of this topic is optimization for supervised models. So in this lecture we are going to cover overfitting, what is the definition of bias and variance, and what is bias variance trade-off. Then we are going to discuss different solutions for the overfitting in the k-fold cross validation, regularization, early stopping, etc. In our earlier lectures we have discussed different training procedure of classifier or a linear regression. Now there is some problem of training. This problem is called overfitting. Now what is overfitting, or better to say, when overfitting occurs? When a machine learning model, it may be a linear regression, it may be a classifier, learns the training data too well. Now this term too well may be that much non-technical, but we have to understand what it technically means. So as of now, what we going to understand about the learning training data too well, that it memorizes the training samples, including their noise and peculiar patterns, rather learning the underlying general patterns that allow it to generalize to new unseen data. Now this is at this moment is bit complicated statement to understand, and in this class we going to understand this phenomena. It's called overfitting. Now we start with our known things. Looks, this is a linear regression problem where these are the data points, and we can hypothesize different kind of function. For example, in this particular example, this is a straight line. It is a simple curve, and it's a very complicated curve. Okay. Now one thing we can observe just seeing the patterns of the data point and the corresponding hypothesis function, that straight line, this is a too simplistic hypothesis function, and maybe this function may not represent the data points that much well. Okay, so this scenario in our next few classes or next few slides, we can say that we can say this is called underfitting, that it is not represent the data points very well. Okay, and the linear regression hypothesis function equation is this is just a straight line equation. Now you go for a bit simple curve. Now you can see that this curve is much better represents the data points, but in both the cases these data points is not been taken into account. Now here another kind of curve. This is a much more complicated curve, order of 4 polynomial. So this is a very complicated curve, and it also considered this. Now one thing we have to understand, ideally when these data points have been given, it coming under this kind of distribution, and this data point is supposed to be a noisy point, or this is a very uncommon pattern, is not very much synchronized with this pattern. But here we can see that this complicated curve, even if this point is maybe a noise, it consider all the points and become very much complicated. So we can say the model complexity is very high here. So what we are basically trying to say in this definition of the overfitting that when a model being very complex and going to consider all the data points, even if a point may not be from the actual distribution, rather from the out of the distribution, then this kind of situation, we said, they learns the training data too well and it memorizes the training samples. They memorize all the samples including their noise and the peculiar patterns, rather learning the underlying general patterns. That means this is the general patterns, and it is basically not only this, it is basically going to, so it's a very complex, becoming complex, and it considers noise also. So this is considered some sort of general pattern, and it lose the generality and going to stand. So if this scenario happen, then we say that our training data is overfitted, or you can say the tendency of overfitted is very high. Now this kind of modeling, when this kind of very complex models are may not be very good to generalize to the new unseen data, because this new unseen data is supposed to come from the given distribution. Okay, so in another case, if we have too many features, so the learned hypothesis function may fit the training set very well. That means this kind of situation, but fail to generalize to the new examples. But it actually not represent the data sample from a particular generic distribution. Rather, it try to memorize all the points, including some points that may be noise. So that is the problem of overfitting. Okay. Now here you can see the similar example of classification problem. In overfitting in classification, you can say this line may not be a very good separator or decision boundary for these two classes. So it may be underfit, not well separator, or not well very good distinguish between these two classes. But rather this may be a much balanced kind of there, so that we can choose this particular. It's not a simple curve kind of thing, but you can say that this is a very much complex curve, very complex curve, and it may be overfitted for this particular classification problem. Okay, so you can say that kind of flowchart kind of thing. So if a model is very performed well on the test data, if it is yes, then it's a very good model. So what is important to note, that the performance of the model on test data is becoming the evaluation metric. But if it is no, if the model perform well for training set, if it is yes, that may be a case of overfitting. So performing well on trained data but not performing well on the test data, in general a clue of overfitting, or in general indicate overfitting. And if it is no, so this model is performing bad for both training and testing, this is typically underfitting. So it's not good. To understand overfitting, we introduce two terms. One is bias, another is variance. So first of all, what is bias? Bias is basically the error of the model prediction. So it is the error from wrong assumption in the model, but is essentially is difference between the model prediction and the target output. So models with high bias are in general very simplistic. The simple models can't represent the data point very well, and such that the bias is very high. And the high bias, the model with high bias always leads to a high error both from training and test data. On the other hand, variance is basically measuring the scatters or spreads of the predictions. So, in general, variance is error from too much sensitivity of the training data. If our model or our model complexity is very high, then it is going to model the training data very well, but it lose its generalization capability. So, it is not that much good of the testing data or any unseen data because it has a less generalization ability. So, the model with high variance always has very low training error, but very high error rates of the testing data. Now, let us try to understand these scenarios, that is bias and variance, on using these bullseye diagrams. So, in case of low bias and low variance, this is the ideal case. What kind of classifier or what kind of predictor we want? So, this prediction is clustered with the bullseye and this scatter is also very low, that means that it is densely clustered. Okay. So, this is an ideal model and it is accurate and consistent. Now, if it is a high bias and low variance, so this case. So, since it is a high bias, then the error this is very high. So, it is not clustered in the bullseye region, somewhere else. That is why it is a high bias, but it is densely clustered because of low variance. So, prediction are densely clustered but not clustered on the bullseye. The model is too simple, result high training error and testing error, and basically this causes underfitting. Next, if the model is low bias, so this case is a low bias and high variance. It is essentially centered to the bullseye, but the spread is very high. So, since this particular model on the training data, it is very accurate, but due to this complexity, very high complexity, it loses the generalization capability on unseen data. So, generally what happened? This model cause very low training error but high testing error, and that is means poor generalization and causing overfitting. And lastly, this high bias and high variance, this is predictions are scattered this because of high variance, and high bias it is not centered bullseye. These models are not very good, both inaccurate and inconsistent. Now, there should be a trade-off between variance and variance, or we can say there is a trade-off between bias and variance. We have to choose the model very judiciously based on bias and variance. So, what we summarize from this observation in last few slides, the model with high bias and low variance is too simple and has a very few parameters, that means less complex. This model often causes underfitting. So, in general, high bias and low variance is not good, and because of it cannot represent the data point well. Now, you can say for a model with a low bias and high variance, that means model are very good in the training, is too good in the training data, but is not at all good with the testing data. So, it loses the generalization capability or ability. These models often cause overfitting. Here you can see in diagrams that this is the bias and this is the variance, this curve. Okay. So, with the model complexity, if it is high, so it is increasing and the bias is decreasing. So, this is very common because of this definition, because if model complexity is high, generally the error, the training error is coming to low, but in the case of if model complexity high, this variance, the scattering is going to high. So, this is some meeting point, this is a very solution zone kind of thing, you can say. Here this is some ideal situation where the total error, this particular thing, is a level that we cannot control it in this way. So this situation or this area is the best solution area or solution. We have to choose the model parameter such a way that our model should lie in this area. Okay, so we have to choose a model which balanced in the low bias and low variance and avoid overfitting as well as underfitting. So the basic idea is that an optimal balance of bias and variance would never overfit and underfit the model, so that we can put this total error is a very minimum position. So let's try to understand the overfitting from a bit analytical viewpoint. So a hypothesis function H is said to be overfitted on training data if there is another hypothesis H bar, which is not essentially the H, such that H bar has more error than H on training data but less error than H on the testing data. So what we understand from this definition, the performance of a classifier on training data may not a good predictor of the classifier or the model itself. What does this mean? That learning a classifier that classifies a training data perfectly may not lead to the classifier with the best generalization performance. It may be very good for the training but may not have very good generalization ability. So testing error is high. So testing performance is bad. Okay. So generally two reasons. The training data is maybe noisy, or the training data is very small. So if you think very simplistically, overfitting occurs when model is too complex and underfitting occurs when model is too simple. That we can very easily understand from these diagrams. This is a very simplistic diagram. This is a straight line and there is a chance of underfitting is high. Whereas this is the model complexity here is very high, so there is a chance of overfit. So here that's why you see overfitting occurs when model is too complex, whereas underfitting occurs when the model is too simple. So what we can conclude, the training error is not a good predictor of the testing error. Now let's consider the total distribution still. Okay, so there is a T is the training set. So what is required? Required is that we have a good generalization ability on this distribution D. Now let's consider H is our hypothesis function and H bar is another hypothesis function, is not equal to H. Now this hypothesis H is overfits on D if the error on training data is less than for this H bar hypothesis function. So what this essentially means, for our hypothesis function doing well on training set than this hypothesis function H bar, but doing bad on the testing set than this function. If this situation occurs, you can say H belongs to space capital H overfits distribution D. Okay. So what is that? The estimate error on full distribution by using the test data sheet. That is a very important thing. How we estimate the error or in other performance over the full distribution by looking at the performance on the test data. If test error is very high, consider our classifier is doing bad. If the performance on test data is good, so very good generalization capability, we can say that our classifier is good. So error on test data, we say generalization error, and we want it low. So most important thing, the generalization to unseen examples of data is what we mostly care about. Now, why this overfitting is very common event in machine learning? First of all, in this train test split, there is a total number of data samples, and we splitting. This is the training data, the testing data. So what we observe that in general more data samples are used for training. Test set are in general too small. So that may be one reason overfitting. Another human tendency is that we generally choose very complex hypothesis function. There is a human tendency that we always think the bigger the model, better the performance. It may not always be the case. Essentially, when the data set, training data set is small, then the complex model has a very much tendency to be overfitted. Okay, so that may be another reason. Now, another the human understanding or human thinking, that we always think like that if a classifier is performing well on training, it's a good classifier. It also perform well on the testing data also. So it's be tough to think a model performing good on training data may get fail on the testing data. This is bit we are not thinking that a model which is performing good in training data may fail. So since sometimes getting good accuracy even in the training data is too hard. So training data is is so complex. So getting this accuracy in the training data itself is tough. We are not thinking about generalization during the training time. So this is the common human thinking. So that's why the data overfitting is a very common. Okay. Now we are going to understand what are the different solutions is possible to prevent or handle this overfitting. Now in this lecture we are going to understand three main methods. First is k-fold cross validation and regularization. Another kind of regularization is called R-stopping. So we start with k-fold cross validation. Now here you can see that in k-fold cross validation, that is a technique which is used to reduce the overfitting by measuring how well a model generalized to the unseen data. So there is two things here. It is used to reduce overfitting first, and how it do this by measuring how well a model generalizes. So what essentially we do in k-fold cross validation is that initially our data set is divided in two parts. One is training set, next testing set. Now training set is divided two parts, training set and validation set. Fine. Now what is our training set? This set and this validation set is basically the thing. Validation set is going to validate how the model is trained. So what we are going to do in our case of k-fold cross validation, the training set has been divided into equal number of partitions. It may be here k partitions. That's why the k-fold. So, and then instead of training and testing the model just once, these equal k parts are training and testing for the k times. So since the training set is been divided in equal k sub folds or groups, so what we'll do, we say the training set always forming in this S minus S1, where S1 is a validation set. So this part is training set and this part is for round 1. Round 2, this part is validation set and rest this part is for training set, and so on to k. So the step-by-step procedure, if you do this, choose a value for k, common choice the 5 to 10 in general. Now split the data set into k folds, training data set in k folds. For each fold, train on k1 fold. So this is the k1 fold, k minus 1 fold. So, and test on the remaining fold. You can see test, that means validate on this, and record the score. In the loop, this is for all k partition or folds, and compute the average score by this. This is S is basically the validation score up to sum it over k folds and by k, average it out, and this will give you an average validation score. Okay. The question is, why this kind of procedure is going to help to reduce overfitting? Now, there is some reasons. First of all, we have to understand reduce overfitting means somehow we have to improve the model's generalization ability. Okay, so k-fold cross validation improve this model generalization ability. But question is why? Okay, because in a single split, that means train and validation data set, or if it is used on a single time, then the model is being evaluated or validated only once. But in the k-fold cross validation, it is evaluated k times and it averages out. So it gives a more reliable estimate on how the model will perform on unseen data. Now, unseen data means what? These different folds. And this prevents overfitting during model selection. So that's why this k-fold cross validation improves the model's generalization ability. So what I said that before it was on one validation set, but in k-fold cross validation is on k different validation set, and this reduces the dependency on a particular split and hence leads to the better generation estimate. Okay. Now again we think in k-fold cross validation, each data sample has been used k minus 1 times for training and once for the validation. They essentially captures, if we do in this kind of repetitive way, the model captures the broader patterns, or we can say the intrinsic properties of the underlying data distribution very well, rather than memorizing a specific subset. And this is what exactly we want. And so it provides a better representation of the true data distribution, and that means the generalization ability is going to be increased. In another way, we can say that single split caused the high variance. Okay, in accuracy estimate, whereas k-fold cross validation lowered the variance performance estimation. Because what we are doing in k-fold cross validation, average the performance over k runs, which smooths out the noise from the smaller unrepresentative samples. So it produces a more generalized estimate. So these are the basic reason why k-fold cross validation helps to model to generalize well, and definitely as a result reduce overfitting. So in summary, what we can say, k-fold cross validation improves generalization because it forces the model to perform well on many different unseen data set, not just one. Okay, our next method of reducing or preventing the overfitting is regularization. So regularization basically helps the model to generalize better. What it essentially do, it penalize the model complexity by adding a penalty term to the loss function of the model. So as you know, the loss function, initially we have this our cost function, basically the original loss. We add a penalty term, okay, and it is multiplied with is called regularization parameter. So this penalty term is added to the loss function, which essentially makes that it helps to remove or reduce the large weights. It discourages the too many features, or it also ensure that model not becoming highly complex or flexible. So what it essentially does, or essentially discourages the large weights, too many features, or the complex model or model complexity too high. And by doing this, they assure that the model is generalized better. Okay. Now, as we said that our loss function is initially the original loss, as we have defined in linear regression, logistic regression. Now we add some penalty to it, and it's multiplied with this lambda. Is a generalization parameter which controls the strength of regularization. Larger the lambda, the model will be simpler. Smaller the lambda, the model will be more complex or flexible. Now, as we said that regularization reduces overfitting by adding a penalty term. And based on the penalty term or type of the penalty term, we can see that two types of regularization. One is called L1 regularization, called lasso. It adds the absolute value of the coefficient as penalty term, absolute value of the coefficient to the loss function. So what does this make? So penalty term, what essentially do? This makes some unimportant weights to exactly 0. So somewhat it select some important features and removing some removing will make it exactly 0. Some unimportant features. And by this we achieve the institutionalization. And this lambda is regulation parameter. In case of L2 regularization, sometimes we reach, it adds the squared value of coefficient to the loss function. So this is squared value of the coefficient. It enforces large weights to decay, but it doesn't make them zero. So it actually not doing the feature selection. Rather, it spread the influence on all the features or across the features. It reduced the reliance on some particular feature and make them important to all the feature important. So spreading influence across the feature. So this is the original loss function, and this is the penalty. Let us try to understand it more in details. In L1 regularization, as we earlier said, that it reduces overfitting by performing feature selection. How do they do feature selection? Adding a penalty term such that some weight it makes the show. Okay, so penalty term is basically absolute value of the models. You see the original loss function, and this is the penalty term. Okay, now L1 regularization achieves automatic feature selection by making some features zero. That means it removes some feature by analyzing less important weights, making them exactly zero. What do you mean by weights making exactly zero? That means we remove the feature. And it reduces overfitting by limiting the model complexity. You can understand very easily. If some feature we just remove, definitely the model complexity will be reduced. And the weights becoming too large. Number of weights will be less. This achieves, it will make the model simpler, and this achieves better generalization of Markov data. Okay, when this kind of regularization is suitable, when data are very high dimensional, and this data has many irrelevant features which may not impact on the decision master or prediction highly, and when we need simpler models. Okay, but L1 regularization is not very suitable when features are highly correlated. Then it is all the features is required, but to some extent they are required. In this case, because L1 regularization is arbitrarily pick, making some features zero, that may not be useful for that. Okay, now come to the L2 regularization. In L2 regularization, so-called ridge regularization or weight decay, reduce the overfitting by penalizing large models weight. So this model to learn small, smooth and stable parameters, and in this case this is the original loss and this is the square is a penalty. So it penalizes large weights. That means squaring weights makes large weights very costly. Okay, so it forces the model to spread the importance across features. So it's decaying some very large weights so that the model is going to depend on all the features, not some very important features, and prevent reliance on few extreme conditions. So that is very important. Okay. Now it reduces overfitting by limiting model complexity. Again, model complexity will be low. Make this model less sensitive to the noise in training data, which achieves better generalization. The answer data. Okay. Now this particular L2 regularization puts the numerical stability when the features are correlated, because we are not going to make them zero weight. That means we are not exclude any features. Rather, we spread the importance across features and prevents reliance on a very few extreme coefficients. Okay, so then that is the very important criteria of auto-regularization. Skips all features, so no sparsity. Coefficient shrinks or decay toward zero, but rarely become exactly zero. Unlike so it doesn't pump the feature selection. Now take a example when this L1 regularization is useful, when L2 regularization is useful. For L1 regularization, it's generally high dimensional data. Automatic feature selection is required, or L1 sets some weights to 0. So take this example. It's a house spice prediction. It's a lot of features like size of house, number of rooms, location, distance to city center, age of house, noise level, postal code indicators, many random and quickly related features, etc. Now here L1 regularization is suitable because these features like noise level, postal code indicators, these are not that much important feature for the house price. So we can make them 0 or remove this. So they can do the feature selection by making some weights 0 for irrelevant feature like distance to city center, age of the house, noise level, postal code indicators, and so on. So ultimately model with sustain with size of the house, number of rooms, location is more interpretable and reduce overfitting since model become very simple. But when L2 is important, if all features are potentially useful, they are correlated, multi-correlated, and don't need exact zero in weights. Suppose the example it is a rain forecast, and the features are atmospheric pressure, humidity, dew point, temperature, wind, cloud cover, radar, etc. These features are very much related to each other, so it's correlated features, and all are important for this rain forecast prediction. So this L1 regulation is suitable here, that it strings all the rain forecast with functionally, so that no single metric dominates but keeps all contributing. And so we can get a robust prediction that doesn't overreact to any one metric. So this is the two examples that we understand when we use the L1 regularization to use the L2 regularization. Now, what is the role of lambda? If lambda is huge, all coefficients rings 0. The model become very simple, almost flatline, and it's going to underfit for both the L1 and L2. When it is very tiny, 0.00001, is almost no penalty applied. Weights become large and to tie model every pattern. Even outliers is being plotted or fitted. The training error is low, test error is high, maybe not perfect. And when it is judicially selected, say moderate kind of thing, the model achieves better generation ability. It can model the intrinsic property of an underlying distribution very well. Complexity not too high, not very simple, so not overfitted nor fitted. So this okay. So these are the way we choose lambda. Okay. Now we just touch upon another way to handle regularization is called stopping. This is you can say kind of regularization, but this is used by training a model with a iterative method such as gradient descent. Now try to understand this thing. This is the epoch and this is the accuracy, model accuracy. to some certain points, after some iteration, you can say that training accuracies keep on increasing, but there is some testing accuracy is basically start decreasing. So there is some generalization error starting. Okay, for this loss also, for some after some epochs, up to some epochs both are reducing, but after some training loss is still reducing, but generalization error or testing error is start increasing. So this position is a good time to stop. So up to this point improves the model performance on data on the test data set, but after that the generalization will start to increase. So we have to understand that in after which epoch or after which iteration we must stop. So early stopping rules provide guidance to how many iterations can be run before the model begins to perfect. So this is the just a very brief overview of the early stopping. Okay. So in this lecture, what we have covered, that concept of word fitting, what is the definition of bias and variance, what is the bias variance trade-off, and then we discuss about solution of word fitting, namely k-fold cross validation, regularization. In the next module, starting network. Thank you.